Alright, so in the last video we talked about the summary so far, and in this video we'll be talking about an example solution, and then we'll also start in on the graphing. So the sample solution, or the sample differential equation we want to look at, is x prime. This is the one that we did the group work on, so you should have hopefully the solution to that already worked out, but we'll go ahead and just briefly run it. So the trace of A here is equal to 1 minus 4, which is minus 3. Determinant is minus 4 plus 6. And so therefore we have lambda squared minus 3, which would be plus 3. By the way, please be careful when you're constructing your characteristic equation, because one small error in that can really lead to massive problems later on. Okay, and so now we will go ahead and factor that out. Because but just as another hint, if you're starting to get really bad numbers, that's probably a sign that something is wrong. Good, so we get lambda equals minus 1 and lambda equals minus 2. And therefore, for lambda equals minus 1, we're putting our system together here. And just like we were saying before, we can do a shortcut, but with this one, let's go ahead and write down our full answer just to be sure. So this is going to be 1 minus 1, which would be 2. And for the second equation, we'll have a 3v1 and minus 4 plus 1 is minus 3, I guess, huh? And of course you'll see that indeed these two equations are constant multiples of each other. And so you could rewrite that as v1 minus v2 equals 0. They're all the same equation, right? And so therefore you could use our shortcut rule or whatever. You can see that a sample representative of this line is the vector 1, 1. Good. And now for lambda equals minus 2, we'll just do our first equation again. So I will have 1 minus 2, that'll be 3v1 minus 2v2 equals 0. And so therefore the vector for that, let's go ahead and write that as v2. This is v1 over here. So that'll be 2, 3. And that's just one sample, right? Because any constant multiple of an eigenvector is also an eigenvector. So those are not uniquely determined. So now we can write down our solution in general. C1 e to the, whoops, go ahead and put in our numbers. Very good. Okay. And now what we want to do is graph this. How would we graph this? So this is probably the most important part of our discussion, our live set. So what we did was we focused on each piece of this solution separately first, and then we put them together. Okay, so let's just take a look at this first piece first. So how would I graph c1 e to the minus t 1, 1 for different values of c1? Well, those are all lying along the vector 1, 1. So if this is the vector 1, 1 here, I'm going to be drawing the line for 1, 1. So that's going to be all the way through here. Right, so there's we can think of that as our 1, 1 there. It's really all the scale multiples. But now notice that if I choose C1, for example, to be equal to 1, then what does my solution look like? I would start here, right, at the point 1, 1, at time 0. Right, and C1 is equal to 1, I'm thinking, so that's just a 1 altogether here. And so then where do I go as time goes into infinity? Well, as time gets large, this part right here, e to the minus t, goes to 0, and so we're going to be going to 0 along the line. so if I started bigger than that, I would also go to 0. And if I started down here, I would also go to 0. And we would go to 0 again on the line. Okay, so this is one solution to our differential equation, right? And then similarly, you could write down the second equation, or second solution to our differential equation. Right? And so that's going to be slightly more steep, right? I'm kind of exaggerating that for effect here. So this is 2, 3. And now what happens to our solutions is just the same. If we start anywhere on this line, we're going to be going towards the origin as time goes to infinity. Now notice that the origin is actually a separate solution, right? For both of these, the origin is a separate solution. That means that if I started off the origin, I would only approach the origin, but I would never actually intersect with it, right? Because, again, for example, if C2 is not equal to 0, then this expression right here is never equal to the origin. It's never equal to 0, 0. It gets very, very close as time gets big, but it's never equal. Okay? Good. So now the question is, I've got these two separate linear equations here. Oops. I want to try to put them together as a single plot. Right? So this is, by the way, the graph here is x1 and x2, right? Oops. x1 and x2. Good. So how do I put these together? I'm going to go ahead and exaggerate the difference between these two vectors here. Oops. Big origin. Okay. Now I know already that this one goes to the origin, this one goes to the origin. Okay. So now the question is, what happens to the sum? Now, if you take a look at the sum here, which of these terms goes to 0 faster than the other? E to the minus 2t, so this term goes to 0 faster, a lot faster, right, than the first term. And the implication of that is that solutions become tangent to the other vector. In other words, solutions going to the origin will become tangent to the vector 1, 1. And so by that I mean, maybe I'll draw these in red. Tangent to 1, 1 means you're going to come in like that, or like that. Okay, so these are also coming into towards the origin. Oops. Oh. Oh gosh. Okay. So yeah. So these other solutions are also going to come in tangent to the 1, 1. Good. All right. And so the other solutions now, you know, even if you're starting way over here, they're still going to come around and hit like that. So, you know, if you're starting way over here, they're still going to try to come around a little bit and try to get tangent with 1, 1. Oops, you can't see that anymore. There you go. And so this kind of a plot here, the origin is representing a sink. Okay. Now I'm going to pause for real, and I'm going to pull up a website and we'll take a look at a direction field for that. Okay, here we go. So I've got the scale kind of stretched out in the upper and lower directions. I'll put this website on our class web page, or the link to our class website, so you can play around with it a little bit. And so you can see here that the solutions are coming in towards 1, 1. And so you can probably see 1, 1 in here. I tried to stretch it apart so we could see the other vector, but it's too close in here. It's really hard to distinguish between the two eigenvectors. But this is what a sink looks like. So you're going to see solutions zooming in so that they're tangent to 1, 1. And so this is a good way of telling where 1, 1 is. The other eigenvector is very close in here. I tried to stretch them apart, but you still can't really see them very well. Okay, so in the next video we'll try not to have any weird things go on with our video, and I'll see you there.